Okay, everyone, I'll get started now. So I'm going to be talking about pre-trained sentence and contextualized word representations this time. This is obviously a thing that is very, very hot and exciting right now in NLP, so I'd like to talk about it. At the same time, it's something that's a little bit confusing, I think, for reasons I'm going to be talking about later. So I'm going to try to give like a kind of systematic explanation of things here. So just to contrast with what we talked about last time, we were talking about neural models where we had word level embedding and prediction, and also kind of sentence level models where we have sentence level embedding and prediction. And we're going to talk about both of them. Last time we talked about non-contextualized models where basically this embedding function is independent regardless of the other words in the sentence. This time we're going to talk about contextualized embedding models where it is dependent on the other words in the sentence. So the goal for today is I'm going to be talking about these two concepts. And I'm going to be talking about tasks and data sets and methods. So like learning tasks or objectives, data sets and methods that are used to be doing that training. Introducing training objectives and talk about multitask and transfer learning from a kind of broader point of view. I talked about up until this point, I've talked about a bunch of things. I've talked about like sentence classification tasks, and I've also talked about, for example, tagging tasks, like tagging, part of speech tagging or named entity recognition. For sentence representations, there's actually a bunch of other things that you can do with them. To go through them briefly before we get on to the actual training methods. The first thing obviously is sentence classification, which we've talked about already. There's other methods that we can, other tasks that we can handle with these models. So one is paraphrase identification, for example. Semantic similarity, entailment, and retrieval. And these are all things that we can do with sentence representations. So in other words, taking a sentence and turning it into a single vector. So sentence classification, we've already talked about this. This is the assignment, so I don't really need to go through this. It's taking in a single sentence and turning it into a label. But there's lots of other things, and one thing that's been particularly widely, used as a method for evaluating these models, and also just as a downstream task that you might want to solve, is sentence pair classification or sentence pair regression, I guess. So an example of a sentence pair classification task is identifying whether A and B mean the same thing. So for example, we could have Charles O. Prince, 53, was named as Mr. Wheel's successor, and Mr. Wheel's longtime confidant, Charles O. Prince, was named as his successor. So do these two sentences mean the same thing? Yes? Yeah, so I guess the answer is basically, right? It's not exactly the same, but it's pretty close. So paraphrase identification basically says, pretty close, they're talking about the same general topic. Maybe you get long-time confident from this one, which you didn't get from this one, but hey, it's close enough. This is a minor piece of information. There's another thing called semantic similarity or relatedness. So semantic similarity and relatedness are basically two different metrics. And this is taking the 0-1 paraphrase identification task and basically turning it into a continuous value. So paraphrase identification, there's in almost any two sentences you're going to have some small nuance that's a little bit different. But semantic similarity is saying, okay, if almost everything is the same, we're going to give it 4.9. So even here, like person and man are different, right? But we're going to give this 4.9. And then we have something like this, which gives you a 3.6. This actually is the opposite, but it still gets a high relatedness score. There's different definitions of semantic similarity that give negations and other things like that, even lower scores. So another way you can ask the question is, how plausible is it that both of these would be true at the same time? Which is more like semantic similarity, and then this case, neither could be true at the same time. So this would get a low score. But there's different metrics for this. And more widely used nowadays is something called textual entailment. It's also called natural language inference. They both basically mean the same thing. And basically the idea is, I guess maybe entailment is the phenomenon and natural language inference is the task of identifying the phenomenon. But entailment is basically, say, a logical connection between two things. If A is true, then B is true. So the woman bought a sandwich for lunch, and the woman bought lunch. A entails B, right? You can think of paraphrase identification as bidirectional entailment. So A entails B, and B entails A, essentially. Oops. Should turn off Slack. On the other hand, contradiction is if A is true, then B is not true. So the woman bought a sandwich for lunch. The woman did not buy a sandwich would be an example of the opposite. A thing is not true. Here, this is also difficult because, let's say the woman bought a sandwich for lunch, and the woman sold a sandwich for lunch. It is possible to both buy a sandwich and sell a sandwich, right? Or John sold Jane a car, and Jane sold John a car. It is possible that both of them sold cars to each other. It's just not very probable. So for a lot of these data sets, it's in the most plausible scenario that you can think of, would this entail this or not? So it's kind of difficult because these come in shades of gray. But then in neutral, you say cannot say either of the above. And so the woman bought a sandwich for lunch, the woman bought a sandwich for dinner. This is much, it's pretty plausible that you might buy a sandwich for both lunch and dinner. You might be a pretty boring person if you did so, but hey, yeah.
What if you switched the order of the entailment example? Is it still entailment?
No, this would be neutral because you couldn't say you bought a sandwich for lunch if you just say you bought lunch. So entailment is inherently directional. Paraphrase identification both have to entail each other. So that's a more a stricter definition. So there are really popular data sets for this, including SNLI, Stanford NLI, and multi-NLI, where NLI is natural language inference, like I mentioned before. There's also XNLI, which does this in multiple directions. So then there's adversarial NLI that tries to prevent it from being easily solvable according to kind of surface level queues and stuff like this. So this is a very popular paradigm to evaluate models nowadays. Now, how do we create models for doing this? There's a bunch of different ways we can do so. One way is to calculate a vector representation and feed the vector representation into a classifier like this. So this is an example, this is another example. You feed both into some sort of classifier and then make a yes-no determination. And then the question becomes, how do we get such a representation? And so one way to do so is to just train end-to-end on this task. But unfortunately, this has the same problem of standard sentence classification models, which is that our classification data is small. and also the feedback from this like yes/no label. You don't know exactly where, you know, like what caused them to be entailment or what caused them to be contradiction, etc. Oh, just a very quick note. This is kind of an auxiliary note, but I think a lot of people might want to do a task like this potentially. So when you're doing tasks like this, one of the most common ways to do this is to take like your vector x1, or let me call it h1, for the hidden state that you get out of your model, h2, and then do h1 element-wise multiply by h2, and h1 minus h2 absolute value. And concatenate all of these together. So basically the intuition here is that like you have two sentences, you want the representation of the first sentence, you want the representation of the second sentence, you want the element-wise multiply, because if you element-wise multiply, things that are similar will get a large value, right? And then you also want the element-wise difference, because if things are very, like a particular element is very different, then that will indicate that the underlying content is different. So this is just one example of a way that you can take two vectors and feed them into a classifier. Okay. So I'm going to talk about ways to get sentence representations and also contextualized word representations. Contextualized word representations are a little bit more straightforward. They're like the things that we would get out of a bidirectional LSTM-based model to do tagging, for example, or a transformer-based model to do attention. So I'm not going to talk about the use cases for those because I feel like we've already talked about them in earlier classes. Okay, any questions so far? Okay. So before I get into this, I'm going to give a little bit of a broader overview over multitask learning in general. And we're going to talk a little bit more about specific methods for multitask learning later. But basically types of learning, so multitask learning is a very broad term. And the very broad term applies to basically anything where you train on multiple tasks. So you have multiple tasks that you care about, and you want to train on them to improve the accuracy on one or the other tasks. This is a relatively old concept. It's not, it's been around since before neural networks and wasn't necessarily applied to neural networks from the very beginning. But neural networks are particularly good for it because neural networks learn underlying representations. So you can use one task where you have lots of data and apply it to another task. Transfer learning is a type of multitask learning, and this is basically where you have multiple tasks, but you really only care about one of the tasks. So you have one task that you want to do well on, you have multiple tasks that you can train on, but you don't care necessarily about doing well on all of the tasks at the same time. You'd rather like to transfer knowledge from one of the high resource tasks to one of the low resource tasks, or easily learnable tasks to less easily learnable tasks. And domain adaptation is a type of transfer learning. And in the case of domain adaptation, the output space is essentially the same, where the underlying task is the same, so the type of predictions that you can make is the same, but the distribution of the inputs and outputs may be different. So like to give an example of transfer learning that's not domain adaptation, it will be just about everything that I talk about for the rest of the time. We take a language modeling task, and then we want to transfer knowledge to a text classification task, for example. So in contrast, domain adaptation would be taking like a machine translation system trained on news text and then adapting it to a biomedical domain, for example. And they're both solving the task of machine translation, but they're doing it in across different domains. So we have many, many tasks in NLP. So only text would be language modeling. There's other ones where we can get lots of naturally occurring data. We don't have to hire anyone to make data for us, usually. So that would be like machine translation or other forms of like weakly supervised learning where, for example, we could get data from Wikipedia, where we're lucky to have Wikipedia and lots of volunteers naturally creating data for us on Wikipedia. Then there's also ones where we need hand-labeled data. So this would be many analysis tasks like named entity recognition, parsing, etc. In general, this is the best one to do transfer learning from. This one's also pretty good to do transfer learning from because we can get lots of data. This one's a little bit less good because we can't get lots of data. On the other hand, only text is definitely less informative than text plus some sort of naturally occurring annotations, and very often hand-labeled annotations are cleaner or easier to work with. So it's a trade-off between amount of data you can get to usefulness of the underlying annotations that you can get. So transfer learning has been done from every single one of these types of tasks. And of course, we're doing this in many languages and many domains. So, even if we can get hand-labeled data for news, we might not be able to get hand-labeled data for another domain. So rule of thumb number 1 is that we want to be doing multitasking to increase data. So, general domain to specific domain, high resource language to low resource language would be one example as well. Plain text to labeled text, so LM to parser. Number 2, it tends to work better when your tasks are related, or at least the information necessary to solve the tasks is similar. To give a very interesting example, there was a paper that used eye gaze data and summarization data. So they basically strapped people into an eye tracker and asked them to read sentences, and you can tell where they focused on when they were reading the sentences or documents. And then they did multitask learning, predicting the eye gaze and predicting summarization, so predicting which words you need to be leaving in a summary. So why is this, useful? Obviously, the parts that people are reading carefully are probably going to be the more important parts, right? The parts that are not, people are not reading carefully are going to be less important. So these two tasks, these two annotations, even though they were collected in very different ways, are going to be correlated in some way. Of course, there's lots of other examples like this. Recently, there's been a very big move of doing language modeling and using language modeling as a general kind of pre-training method for multitask learning. And so why is this a good idea? I think the good idea is because in order to predict the next word well, you need to know a lot of things, right? You need to know syntax, you need to know semantics. So like, for example, you need to know syntax to just get the part of speech correct for the next word, right? You need to know semantics kind of on a high level because you need to know I dissolved. You have I dissolved the or something like that. So in order to predict the next word in that sequence, you need to know things that tend to be dissolved by humans, right? And it could be the ice cube, not ice cube, sorry, the medicine in water or something like that, or it could be the company or the group or something like this. So you're learning a whole bunch of things that tend to be selectional preferences. You also need to know formality of language, for example. So you're not going to suddenly start using very formal words in an informal text. Can anyone think of things that you can't easily learn from a language model? Yeah.
Something that captures long-term relationships, say something like XYZ plays basketball, and then maybe you can say that he's in this position, or like say soccer is at this position, but that suddenly changed the context. So anyone might not be able to say that even if he's a forward player, and we say that he was defense, might still not be.
Mm-hmm. Something that captures long-term relationships. So that sounds like a good idea. Maybe I'll go one step further. And why do you think a language modeling objective would not allow you to learn something like that? So if it is necessary to use long-term information to predict that, then maybe.
Basically, you require knowledge about the domain, and like based on the training data, say we're talking about a specific sport, it is extremely rare about the amount of data it requires that it can create relationships about the knowledge, the real world knowledge.
Mm-hmm.
So if you don't have any real world knowledge, or the LM does not have a real world knowledge about it, so you won't be able to predict.
Yeah, so I think this is a good point. I think this is a little bit vague there, but to give another example of a long-term relationship that you wouldn't be able to learn very much from, if there are long-term relationships, but they're so rare, it's so rare that they're necessary to predict the next word effectively, then you're not going to be able to learn to use them very well, right? So, like, for example, if 99.5% of the time you can predict the word without looking very far back in the document, it's going to be easier for the language model to predict, based on a very short distance. So that would be one example. If there's not very much data in the domain of interest, that would be another example. To give a final example, language models aren't very good at predicting facts. So one example of a fact would be like where are people born? And the only time you're going to be able to memorize a fact using a language model objective is if it is necessary to know that fact in order to predict the word. So to give an example, X is a French painter who was born in Paris, or something like that. So you have X is a French painter who was born in Paris. Maybe most French painters are born in Paris. So once you know French painter, you can predict Paris without even looking at that person's name. So you get no gradient flow back into the model to say this person was actually born in Paris. If you get X was a French painter who was born in New York, that's a bit unusual, right? So in order to predict New York, you'd have to remember the exception about that particular painter. So an important thing to think about when you're thinking about pre-training or things like this is the models will take any shortcuts they can to learn, in the easiest way possible, reduce the loss in the easiest way possible. So if there's some alternative way to reduce the loss without learning the thing that you want them to learn, then it's not going to be a very effective way of learning. So that's something just to think about here. So anyway, moving on. Standard multitask learning trains representations to do well on multiple tasks at once. So you basically take everything and throw things in there, train on both ones at once. A really simple way to do this is randomly choose a mini batch from one of the two tasks and train on it. There's other more complicated ways, but we won't talk about that now. Many examples of this. Kind of the first big paper on neural networks for NLP in kind of the modern era, Colbert and Weston did multitask learning as one of their key ingredients. Pre-training. So here you first train on one task and then train on another. So you train on translation or language modeling, and then you initialize the encoder to train on tagging. This is widely used in word embeddings or pre-training sentence encoders or contextualized word embeddings. So the reason why this is useful is nowadays people pre-train these things on huge amounts of data. So if we had to do this every time through pure multitask learning, we would no longer live in a world where it was habitable because global warming would have been so bad that we couldn't live here anymore. So the idea is basically we spend a huge amount of compute to pre-train on some task that we can pre-train on, and then we don't have to use as much for fine-tuning. Which is better? Is pre-training better or multitask learning better? The answer is standard unconstrained multitask learning is always going to be better, right? Because pre-training is a special instance of this, where we have a training schedule where we first train on one task and then train on another task. So, not restricting yourself to doing pre-training is going to be the better choice, but of course there's computational considerations. Yeah.
What is the objective in this kind of, the previous kind of setup? Do you stop when you're, say, the loss for tagging is like equal up?
Oh yeah, so how do you do like early stopping or something like that? Yeah, you could stop when the tagging loss gets the best. So, but anyway, I'm going to be mainly talking about pre-training this time because this is what's widely used in learning of sentence representations, etc. So, okay. So another thing is, before I go into the details of individual methods, I think thinking about this on a higher level is probably a good idea. So many methods have cool names like skip thought, para NMT, Cove, Elmo, BERT, Roberta, Electra, whatever. I blame this all on skip thought vectors because they were the first to kind of do this. But so this is catchy. It makes it easy to talk about them. But one thing that's really important to remember is whenever we talk about these things, we're talking about three things. We're talking about the model, which is the underlying network architecture. We're talking about the training objective that's used to train the parameters of the model. And we're talking about the data, which is what data the authors chose to use to train the model. However, when people say, well, so how does BERT compare to Electra? Or something like that. Or no, let me give another example. How does Elmo compare to BERT? The question becomes very complicated because the model is different, the training objective is different, and the data they trained on was different, right? So it makes it difficult to isolate, like which one of these is actually contributing. Oh, and actually the way you use the underlying representations is also different. So that's another thing that I can talk about in a second. So unfortunately, these are often conflated, which makes comparisons between the methods difficult. So I'm going to try to deconflate them to some extent in my slides today. So yeah, end-to-end learning versus pre-training. I talked about it already, so I'll skip that. Okay. So now first I'm going to be talking about training sentence representations, and the reason why I'm going to be talking about this first is partly for historical reasons. These started out before the contextualized word representations. But also because conceptually it's a little bit simpler, and the methods that are used to train them also tend to be a little bit simpler. So kind of the story of pre-training or large-scale pre-training in natural language processing probably started with this paper by Diane Le, 2015. And basically what they did was they did something that you guys already know to do, how to do it in this class. They took an LSTM, a big LSTM, and they used it to perform language modeling. So they basically just used it to predict the next word in the sentence. And they trained the model either on the classification training data that they were using for a text classifier, or on a big extra set of Amazon reviews. The model, I don't even know if I needed this diagram, it's just the LSTM. Without even LSTM written here, but basically they just predicted the next word in the sentence, and they tested it downstream on text classification. They initialized the weights of the LSTM for text classification, and they continued training on the text classification task for sentiment analysis. And the results were really good. Basically what they showed was that by training on this language modeling objective, that allowed them to improve results on text classification by a whole lot. And suddenly this LSTM, which was supposedly not very good for text classification, if you pre-trained it in this appropriate way, did quite well. So they showed that it beat CNN-based models, etc. Interestingly, this was the case even if they kept the data the same. So even if they kept the training data the same for the text classifier and the pre-training. And the reason why is basically just the gradient information that you get from predicting the next word at every time step is just a lot stronger, a lot more informative than a single yes or no label from the text classifier data itself that you get at the very end of the sentence. So I think this is a good result, and they kind of deconflated the problem of data. And then, of course, if you train it on Amazon reviews, you do a lot better. You have a lot more data. You learn rare vocabulary better, etc. So yeah. So another thing. This was actually a little bit later than the previous model in many of the models I'm going to talk about. But it's interesting because basically it's the same thing. So the model itself is basically a masked self-attention model that does left to right prediction. So it's a language model exactly like the transformer translation model that I talked about before, except there's no input. So it's just a language model. It's just conditioning on the previous words, and it predicts the next word from left to right. So it's exactly the same, except they took the LSTM and they replaced it with a transformer. But they also replaced the data, right? So they took this data, they took a much bigger data set because it's now 2018 and we know how to train on these bigger data sets. And they showed that this works well on a lot of different tasks. So I think this isn't necessarily, really impressive, like a new insight other than the empirical results. So on some tasks, they just did normal fine-tuning. On other tasks, like for multi-sentence classification, they tuned it on the multi-sentence classification objectives. So either way, it's almost identical to the previous one that I talked about. But the reason why I put this here instead of like different places is I wanted to like demonstrate, conceptually, the first two are the same. This one's different. This one's the same. This one's different. This one's basically the same as the previous example. So I'm going to make connections like this. So okay, another example is autoencoding. So this is another thing you might think of doing. And basically the idea is instead of taking the language modeling objective, you have an autoencoder. So the basic idea here is you take the input, you encode it into one vector, and you take this vector and you predict the output. So here the model is the same as the previous one. The objective is a little bit different. The data is the same as this. And they compared this using it in the same way as before, except they took the encoder rather than the decoder. I don't remember the results so carefully, but if I remember correctly, this was a little bit worse than just training with the language modeling objective, which I think is kind of interesting. I think perhaps part of the reason why it's a little bit worse is because essentially with the language modeling objective, with this objective, once you have looked at like W, it makes it relatively easy to predict X. So you can just look at the fact that you read in W and predicted X, and this like vector here becomes less informative by the time you get to the end of the sentence. Whereas if you encode all of these things, your gradient flow to each example, to each vector in this entire encoder is going to be coming from all of the predictions that you made in the sentence. So basically, let me put it a slightly different way. In this case, the gradient just needs to flow back through the language model itself. In this case, the gradient flow needs to essentially flow back through the entire encoder, and then it needs to also flow back through the entire decoder. Then it also needs to flow back through the encoder in order to update the weights here. And that makes it a little bit harder to learn because you have longer distance connections here. So this demonstrates two things. It does a comparison between them in the same model class. So this autoencoder itself was not super effective. It wasn't a super effective method for learning. But one method that was very effective and was kind of the standard in sentence modeling for a while was context prediction. And this is what was called skip thought vectors, or what I guess it's still called skip thought vectors. You can still download them if you want. But basically, this was LSTM. You had an LSTM model that read into input, and then you predicted the surrounding sentences. So you would read into input, and then you had a corpus of books where you had the next sentence and the previous sentence, and based on this, you tried to predict what you would get here and what you would get here, what you would get before and what you would get after. So this is kind of interesting. It's kind of like word to vec. The like skip thought, skip Graham model in word to vec, except it's like skip sentence. But because skip sentence isn't cool enough, they decided to call it skip thought. But you know, it's like that. And so basically what they did was they trained a logistic, they use this for like sentence pair classification or other things like this, and trained a logistic regression on this model. I guess maybe this is where the vector trick that I talked about before came from. But yeah, there was this. So this proved quite effective. It can be trained only on monolingual data, and it's a good way to get individual sentence representations out of it. So another method that has proven quite good, especially for tasks that have to do with identifying like semantic similarity or paraphrasing, is actually training on paraphrases themselves. And basically what you try to do is you try to predict whether two phrases are paraphrases or not. And then the way they did this is with this, this data from paraphrase.org. It's called the Paraphrase database. And what this looks like is essentially this. So you can put no results were found. So you can put in like bucket, pail. You can put in bucket and you get like pail, basket, cube. That's kind of that's kind of strange, but yeah. I've contributed my to the research community for today. But they also have multi-word phrases. I'm not sure why I couldn't get kick the bucket when I searched here, but they also have multi-word phrases that you can use. And basically the idea of this, this work here is you try to specifically identify whether two phrases are paraphrases or not. And so what you do is you have a paraphrase, and then you have a whole bunch of negative samples where you might do hard negative sample mining, and you try to identify whether these are paraphrases or not. And this still is a very nice method that works well for like sentence similarity. It works better than BERT, for example. Yeah. So one interesting thing here is they actually tried many different models. They tried LSTMs, they tried deep averaging networks, they tried embedding averaging. And interestingly, LSTMs worked quite well on in-domain data, but word averaging methods generalize better to out-of-domain data. So there's, if you look at these big transformer models, there's also a question about whether these will work robustly on other data sets as well. So this method was scaled up to larger paraphrase data. So they automatically constructed a large paraphrase database by getting a large parallel corpus, translating the check back into English using a state-of-the-art neural machine translation model. They got this huge corpus that includes lots of noise, but then they trained kind of a filterer to filter out some of them and left 30 million that are kind of high quality sentences. And they trained using the same objective on this, which gave you like sentence level, sentence similarity metrics that you could use kind of out of the box. So one interesting thing note about this previous result here is as a side effect of two things. One thing is leaderboard chasing. So like people want to improve their metrics on leaderboards. They come up with a new embedding method. They want to beat everybody. Another thing is people conflating this model objective and training data thing. It's very common to see pre-trained embedding methods being trained on data that's very, very similar to exactly the data that's used in leaderboards for evaluation on supervised tasks. So like, for example, if you have the glue benchmark or the super glue benchmark or something like this, they have Wikipedia data, they have news data, and then they have like social media data or something like that included in there. And then you look at the data that was used to pre-train pre-trained embeddings, that includes news data, it includes Wikipedia data, and it includes open subtitles. And open subtitles is kind of like a informal speech data set of subtitles that are used. So, if you want to boost your pre-trained methods accuracy, a really good thing to do is just add a whole bunch of modeling, a whole bunch of like unannotated data in the domain that you're interested in testing on. Unfortunately, Glue doesn't include biomedical text. It doesn't include academic papers, etc. So all of the people who are chasing the leaderboards will not train on this text because they don't care. This is something to be aware of. Like look at the data that things are being trained on, and very often it is. It's not, it will match certain domains, but it won't match, your biomedical text or whatever. Long story short, if you really want a good pre-trained embedding for a new domain, either you have to train it yourself, or you have to make a popular leaderboard that includes data from that domain, and then Google will do it for you. So pick your poison. You get your choice of how to get your good embeddings. So the next, another thing that's kind of notable is this method of infercent. And basically, previous objectives used no human labels. But what if supervised training for a task such as entailment learns generalizable embeddings? So you could think in two ways, like I mentioned before. So one, the task could be more difficult and required capturing nuance, which would mean that maybe yes, you can do a better job here, or the data is much smaller, so the answer could be no. So in this infercent, they basically used a BIOS-STAM model plus max pooling over is their model. Is their data, they use Stanford NLI plus multi-NLI. And the result was that they found this tended to be better than unsupervised objectives, such as skip thought, at a number of downstream sentence tasks. So I think this is an interesting result, and it indicates that yes, we do need to be worrying about like, what kind of tasks we're training on. That being said, now everybody is just training on unsupervised tasks again, mostly. You can take this result for what it's worth, and maybe we should revisit this now that we have better model architectures, bigger data, and see if this result still holds. So, fortunately, this is also easy to do because the data is a lot smaller, so you could conceivably run this on your own like data sets, etc. Okay. So this was kind of an overview. I think this was probably a lot of information, but you can go back and look at the slides and stuff like this and compare them. Are there any questions so far? Okay. Yes.
Word averaging, which I'm not exactly sure what that was. 3 slides ago,
Yeah.
word averaging.
Oh, word averaging, this is like the continuous bag of words model that I talked about before. So you basically take words, word embeddings, and you average them together. So this has no concept of whatsoever of word order. It has no concept whatsoever of compositionality or whatever. However, it can be very good at identifying important words in the sentence. You know, which words are content words, which words are sentence words. It has a very short gradient path between the input side and the output side. So.
Does it make sense to average the embeddings? Because, like, say we have 10 different words and we have 10 different embeddings, does it make sense to average the embeddings?
Does it make sense to average them? Yeah, I think it does. Basically, the embeddings tell you. So, like, to give a really like contrived example, I guess. Like, let's say they were all one-hot vectors. They were like, we didn't use embeddings, but rather used one-hot vectors. We average all of them, and that basically tells us, you know, like which words are in the sentence, right? Another thing, you could sum them together. That would just like give you the number of. That would just give you basically the number and the type of words that were in the sentence. So it gives you a little bit more. It gives you a little bit more information, but it also makes the scales very different for longer sentences and shorter sentences, which might make the model harder to learn. So, yeah. Okay, so I'll move on to contextualized word representations. Contextualized word representations basically, instead of one vector per sentence, we have one vector per word. There's a number of ways we could use these. The first one is just for like single classification tasks, single word classification tasks, so like part of speech tagging or named entity recognition, which I've talked about before. You could also use them for sentence classification tasks where you do some sort of, combination. Maybe you do max pooling, or maybe you do attention or something like that. And you can also use them for sentence pair classification tasks. So there's a bunch of different ways you could use them. How do you train these embeddings? So the first way you can do this is you can do basically what word2vec did, but just instead of doing word2vec with a kind of word averaging model, you do an LSTM or some other model that's dependent on all of the words in the sentence. So basically what this is you take a left-pointing LSTM, you take a right-pointing LSTM. You don't take any of the information about the word itself. So you take one step to the left with the forward LSTM, one step to the right with the backward LSTM. You concatenate them together, you put them through an MLP, and you try to predict the word in the middle. So it's basically word2vec, right? It's a word2vec SIBO model, except instead of SIBO, it's just an LSTM on either side. So this, they trained on the 2 billion word UK WAC corpus and showed very good results. They used the vector for like sentence completion, so predicting the hidden word, word sense disambiguation, etc. So this was kind of the first like contextualized word representation learning model. Another way that you could train a model like this would be using machine translation. So you have multi-layer bidirectional LSTM, But instead of training it to predict the words in the sentence itself, you rather use it to predict the words in the in another model. Sorry, in another language, for example. So in this case, they did English-German. They trained it on 7 million sentence pairs, and then they took the encoder and they used this to make the predictions of the output. You could also use it to have a bi-attention network over sentence pairs for classification. I won't go into details about this, but if you wanted to do sentence pair classification, you could do attention over both. And actually, I think we might have briefly talked about this in the CNN lecture as well. So basically, the difference here is the model is the same between these two methods. It's a bidirectional LSTM. And the only difference is they're training it for machine translation here as opposed to language model. So another thing that you could do is you could train a bidirectional language modeling objective. And this is ELMO. So this is, again, a multi-layer bidirectional LSTM. So model is exactly the same. But the difference was they predict the next word left to right and the next word right to left independently. So in contrast, Contextual, which fed in both, this one just trained it in both directions. So, minor difference, but there's that. They trained it on the 1 billion word benchmark LM dataset. And one key difference here is that they actually fine-tuned the weights of a linear combination of the layers on a downstream task. So they had many different layers, and they did a linear combination of the different layers. And the motivation for this is basically that different information can be captured in different layers of the representation. So for example, in the lower layers, it's very common for more kind of syntactic-y type information, like what is the part of speech of this word to be captured. In the higher layers, it tends to be more semantic-y type information. So, like what is the semantic class of this word, etc., to be captured. So some tasks would prefer semantic-y information, some tasks would prefer syntactic-y information. So you just do a linear combination of these and fine-tune that linear combination. So interestingly, like ELMO is what kind of really made this a really popular paradigm to be using. Why is this? I'm not actually really sure. The methods are pretty similar, but I think probably the biggest reason was that this tested on tasks that people weren't quite as word sense disambiguation. Like it's kind of an interesting task, but it's not like a really clear downstream task. This was more like semantic role labeling, kind of squad type question answering, other tasks that people were more familiar with. But I think they're pretty similar and they weren't trained on the same data, so it's pretty hard to tell like which one is actually better methodologically. Okay, so let's move to BERT. So BERT, I think a lot of people know about. This is doing masked word prediction. So masked word prediction is essentially the same thing as Contextual. So what Contextual did, as you remember, it removed the actual word itself from any context that you're allowed to use, and it tried to predict the central word. And it processed based on this. However, there's a big problem with this method. And the big problem with this method is the left context, even if this is a deep LSTM, it can only look at the left context. The right context, even if it's a deep LSTM, it can only look at the right context. So you're not allowed to look, you're not allowed to like take information from this LSTM and feed it into this LSTM in the next layer. And the reason why is essentially because then that would make the prediction problem too easy. You would pass information from left LSTM layer 1 to right LSTM layer 2, and then right LSTM layer 2 would just say, here you go, here's the identity of the word, and you would it wouldn't be a hard prediction problem anymore. So kind of the ingenious thing about BERT is they figured out how to fix this problem. And the way they fixed the problem is by doing masked word prediction. And basically, the way it works is 15% of the time, you take a word in the input and you say, this is the word that I want to predict. And so you predict those 15% of the words. So like, let's say you randomly sampled dog and you also sampled like likes. It's the words you wanted to predict. So when you did that, you would have dog, you would mask out the input word. So you would mask out the input for dog in likes. And then you would run all of these through all of the layers of your transformer and predict the output. So why is this good? Basically what this means is you've masked out the input. So obviously it's a hard prediction problem. It's not included in your input whatsoever. But all the other words can interact with each other in any way they want, right? You can pass information from left to right, right to left, whatever. So I think, formulating instead of a like encode the context, make the prediction problem, but rather a masked language modeling problem makes this efficient to train, and it allows you to combine information from all of them. So they also have a next sentence prediction objective. So this is skip thought, basically. This is the skip thought objective. The only difference is in the skip thought vectors, they tried to generate the next sentence, whereas here they're just trying to classify whether it's a next sentence or not, given like a distractor sentence. So it's like, it's almost like a combination of the paraphrase identification objective that I talked about and the skip thought objective, where instead of identifying paraphrases, you're identifying next sentences. So, so BERT, is heavily inspired by a lot of the previous work, but it also fixes a lot of the problems. They also kind of have a clever way to do masking. So 80% of the time, you substitute the input word with this like mask, which is basically like, I don't know what this word is. 10% of the time, you substitute the input word with a random word. So you're inputting a random word and trying to fix it. This is something called a denoising autoencoder. So a denoising autoencoder, basically what it does is it takes in an input that has been noised in some way and generates the output. And then 10% of the time, there's no change at all of the word. So you feed in the word itself and you try to predict the word. But the kind of like ingenious thing here is adding the no change thing here means that you can't entirely forget the identity of the word, right? If you forget the identity of the word, you're paying a big price because 10% of the time you're just going to be right by remembering the identity of the word. However, you also need to identify whether that's noise, and you also need to be able to predict even if it's masked out. So I think this is a very like well, created training objective. Yeah, so it's like context detect, but much better suited for multi-layer self-attention. Yeah, so this is the consecutive sentence prediction objective. So you feed in these two, and you make a prediction of either like these are consecutive or they're not consecutive. So if this is the case, then these are consecutive in the books corpus, and if these are not, it's just like a randomly sampled incoherent sentence. Finally, we have this CLS token. And the CLS token here is how we actually make the prediction. So this stands for like your classifier token. And basically what you do is you take the representation for this token after running it through all the layers of self-attention, and then you use this to make this not next or is next prediction. The reason why this is nice is it also gives you a very natural way to apply this to downstream tasks. So you either feed in a sentence or you feed in two sentences separated by a separator into BERT, and then you take the class token and you try to make your prediction. And you can even fine-tune all the parameters of BERT when you're making this prediction. So the reason why this is good is because now you have a very natural way to connect your pre-training objective with your like a downstream text classification objective. Okay, and this is This is great. Notably, this was trained on the books corpus plus English Wikipedia. So now we have more data. Now we have Wikipedia data for all those tasks that need Wikipedia. So, BERT is benefiting both from the model itself, but also from this. They do have a comparison against a purely unidirectional model, so the OpenAI GPT model, and show that this works convincingly better. So bidirectional context is important. But yeah. Okay. Any questions about this? Yes.
Has anyone tried to do the reverse? Once given the contextual embedding, trying to predict the word?
Given the contextual embedding, try to predict the word. That's what.
Decontextualize the word. So given contextual embeddings, obtained through BERT, kind of going back to the words.
So given contextual embeddings from BERT, trying to reverse the words. There is a paper. So the question was, can you take the BERT embeddings and decode the original words? The answer is yes. There's a couple papers I can think of. I'll try to get to this before the class is over, because there's a really interesting paper that I'd like to mention, and it's good for comparing these embeddings. So I'll try to go through the other ones. So since Elmo and BERT made this pre-training very popular, there's lots of other methods that have been proposed. I'm going to try to go through just a few of them. Roberta. So Roberta is BERT model. BERT objective, but they just trained for longer. And they also dropped the sentence prediction objective. I was surprised by this, but they removed like one of the BERT objectives, which is the next sentence prediction one. They trained on, wait, sorry, this data is not wrong. They also trained on more data as well. I am forgetting exactly the corpus they used there. So this is more data than BERT, so that's important. In results, the results are empirically much better. So like basically what this paper tells you is that BERT wasn't trained for long enough and it works well with more data. I've not seen any paper where BERT does better than Roberta, and it's the same model, so you should just use Roberta if you're using BERT. Like, I can't, unless somebody proves me wrong, like there's no reason to use BERT instead of Roberta. So another interesting paper from very recently is this Electra paper. And the model, underlying model is the same as BERT, it's just transformers. But the objective is a bit different. So here, basically what they're doing is they're taking a generator where you take in a sentence, you randomly sample words according to a small masked language model, so like small BERT or something like that. And then you might get the word the, which follows the distribution, but you also might get a word car, where an artist selling a car is like a little bit less likely than an artist selling a painting. And then basically what you try to do is you try to predict in the pre-training objective whether this word is the same as the original or whether it has been replaced by something else. So this is kind of interesting. The reason why this is interesting is BERT only gets a loss function for 15% of the words in the input on average, because you're masking out 15% of the words. This gets a loss function for all of the words every time. So that's kind of nice. And empirically, they show that the data they use the same as BERT or XLNet, which I'm going to be talking about next time. But the result is that the training is much more efficient. So I think this is a kind of nice thing if you're thinking about pre-training embeddings yourselves. because obviously like computational resources are going to be an issue unless you work at like Google or Facebook or something like that. So you know, being able to train 5 times faster is something that's pretty attractive, I guess. So another example is XLNet. So XLNet is a method that is the same as BERT, but it includes a longer context. I'm not going to talk about exactly how this works, because I'm going to talk about it in a future class, but basically the idea is instead of BERT, which just encodes the current segment like this, and then uses the representation calculated over the current segment, you also use the previous segment encoded by the model when calculating the representations for the current segment. So you basically cache the representations from the previous mini batch and you use them in calculation of the next mini batch. And this is kind of like truncated backprop through time, like I talked about. So you basically calculate the representations and use them when you calculate the next mini batch. And this allows you to handle much longer context, you know, theoretically infinite context, because when you calculated these representations, you also used the representations from the previous mini batch. So this is called Transformer XL. This was used in a language model, but it's also used in XLNet. So they also, one difference is that they predict words in order. So this is an autoregressive model. It's not like BERT. You're actually predicting the words one at a time in order. The only difference is that you're actually predicting them in a different order every time. So basically the idea is instead of predicting them from left to right, you randomly sample in order that you want to do prediction in, and then you predict the words in that randomly sampled order. So the interesting thing is this is still a standard language model. It's still a language model that can predict words left to right. You could use it to generate text if you wanted to. But it also can handle bidirectional context. So that's kind of an interesting twist. They trained this on lots of data, 39 billion tokens from books, Wikipedia, and the web. And it did better, kind of unsurprisingly. You know, it's trained on, you know, 39 times more data or something like this. But they also, I don't know if they put it in the actual paper or just a blog post, but they also did an ablation where they trained it on the same amount of data as BERT and showed that it was still helping. And most of that came from this including longer context part. So that is important as well.
Do you still get the linear interpolation or like the vector space seen in this kind of contextualized? What is it?
Do you still get a linear interpretation of the vector space? So can you like linearly interpolate things? That's a good question. I'm trying to think of any results that I can think about with that, and I can't immediately think of one off the top of my head. Does anyone have a?
No, I have another question.
Okay. Does anyone know any results regarding like the linearity or nonlinearity of the vector spaces in contextualized representations? I can't think of any results like that. That's a good question. I can't think of any off the top of my head. Yeah.
I actually don't understand the objective function for this.
Okay, so this is a language modeling objective. A normal language modeling objective, what it does is it predicts words from left to right, right? The transformer can do this too. The way it does it is masking out all of the previous contexts. What this does here is instead of sampling left to right, so like let's say we had 1, 2, 3, 4, 5, 6, 7, 8. And this is the order that we normally predict in, 1, 2, 3, 4, 5, 6, 7, 8. Instead, they shuffle the order. So it becomes like 7, 2, 5, 4, 3, 1, you know, etc. And then they predict in this order. So first they predict the 7th word, then they predict the 2nd word, then they predict the 5th word, like this. So the reason why this is good is basically like if you want to calculate contextualized representation that can access things on the left and on the right, having, 7, 2, 5, 4, 3, so we have 6, and then, let's do 8, and then 6. Up to this point, when you predict 6, it would be beneficial to have encoded all the other information other than 6, right? So you get a model that is able to encode left context and right context, despite the fact that it's still a language model. So I think maybe the thing that I like more about this than like the fact that it's good as a pre-training objective is that it's still actually a language model. So if you wanted to use it as a language model, you could still like generate text from it in a left-to-right manner or something like this.
I have a follow-up question. And a language model tells you the probability of a sequence of words, right?
Mm-hmm.
So if I say that my name is XYZ and I shuffle the words, would this model give me the same probability?
No, and the reason why is because you still have positional encoding, so you know like which words came to the left and which words came to the right. So yeah, no. Okay, so very quickly I'd like to talk about which method is better. And I think you might have kind of figured this out as I've been talking. So which model works best? And the answer is it's not super clear. I think the community has kind of settled on transformers because they're fast. Some results have shown that simple word averaging is more robust than out of domain. There's unidirectional versus bidirectional transformers. There's no comparison to LSTMs, maybe for performance reasons. So this XLNet, they showed that having longer context is useful, etc. I think basically there's not really a super extensive comparison here, but kind of, in some cases people do a few ablations. Which training objective? Again, there's not a very extensive comparison. One nice one is that Zhang and Bowman control for training data, and they find that bidirectional LM seems better than an MT encoder. This is actually not very surprising to me as a machine translation person, and the reason why is in machine translation, actually the decoder is very, very important. The decoder is, generating fluent text, etc. I think you get lots of gradient flowing into the decoder. And because of this, the encoder is actually a little bit less important. It has to, do maybe a little bit of word sense disambiguation, etc. But you can actually get away with a very good decoder and a very weak encoder. So the more pressure you put on the thing that's generating the representations, probably the better. Devlin et al. Find the next sentence prediction objective is a good complement to the LM objective. The Roberta paper finds that it's not. And then which data? Not very extensive comparison. More data is better. So they did a controlled experiment here that shows that more data is better. The XLNet paper showed improvements by adding more data from the web, but actually this wasn't 100% consistent. It didn't 100% improve over every single task they tried on. So maybe focused data on Wikipedia is actually better than others. Data with context is probably essential because a lot of the decision making we need to do in NLP tasks is contextual. So before I finish, I'd like to very quickly introduce a paper. It's called something like the bottom-up evolution of representations. So this paper is a very interesting paper in that it doesn't compare accuracy-wise, but it compares the information included in the representations on different layers of different training objectives. And they compare the BERT style mass-style M objective, the language modeling objective, left to right language modeling objective, and a MT encoder. And the most interesting figure here, sorry, that's small and I can't zoom easily, is they have a method for calculating the mutual information between the representation and the word at that position. And basically, the blue one is the machine translation encoder. The red one is the language modeling. objective, left to right language modeling objective, and the yellow one is the BERT style masked language modeling objective. And you can see the language model. At the very beginning, you have the most information about the current word, and in the farther layers, you have the least information about the current word. The MT encoder is similar, except it still keeps around a little bit of information. The BERT objective actually dips and then then keeps information around at the very last layers. I would give a quiz if we had time, but we don't, so I'll just explain why this happens. So LMs, when you predict the next word, the most important thing is to have good representations of the next word, right? So near the softmax, you want to be able to predict the next word. So by doing that, you can have completely forgotten the previous word as long as you can predict the next word well. The MT encoder, it's still useful to have information about what word it is. It's more important to have information about what word it is in the target language, but it's still important to have, what word it is in the target language is highly associated with what word it is in the source language. For BERT, you still need to know what word it is in that language at the end because you need to predict that word itself some of the time, right? So, so you can see how kind of our different objectives mold what kind of information we have sticking around in our model. So this is a highly recommended paper. There's the title if you want to take a look. So, okay, sorry, I'm over time, but I'll finish up here. So thanks a lot.